Welcome, curious minds, to another deep dive. Have you ever used an application, maybe one you rely on daily, and it just
Yeah,
works?
flawlessly, almost intuitively.
Exactly. Or perhaps you've hit that wall of frustration with a system that crashes, freezes, or just stubbornly refuses to behave, leaving you thinking, seriously, how was this even put together?
Right.
Today, we're not just admiring the magic or lamenting the mess, we're pulling back the curtain on the incredible world of software engineering to reveal the deliberate choices that separate the brilliant from the buggy.
That's really the core of it. I mean, whether you're gearing up for a new project yourself, maybe trying to demystify the tech behind your favorite applications, or simply indulging the insatiable curiosity about how digital worlds are constructed,
Uh-huh.
this deep dive is designed as your shortcut. We've extracted the most vital nuggets of insight from a stack of rich sources to illuminate the essential concepts, principles, and practices that underpin robust software development.
Our mission today is to truly unpack the very essence of software creation. We'll begin our journey with the initial blueprints, the powerful models that engineers use to design systems before they even type a single line of code.
That's the crucial first step.
From there, we'll dive into how they structure their creations, breaking down the fundamental building blocks like classes and their intricate relationships.
The nuts and bolts, essentially.
Next, we'll explore the guiding principles and proven patterns that lead to truly good, resilient software. And finally, we'll peel back the layers on how quality is ensured through rigorous, intelligent testing.
It's a fascinating blend of theory and intensely practical application, I think.
And I promise you, by the end, you'll look at every piece of software you touch with a new, enlightened perspective. Let's unpack this.
So we begin our exploration at the very genesis of any significant software system, the concept of modeling. Think of it as creating the architectural blueprints long before you even consider laying a single brick.
I find this fascinating because it's something we do naturally in life all the time, simplifying complexity. What exactly is a model in this context in software engineering?
Okay, so at its core, a model is an abstraction. It's a simplified yet precise representation of a complex problem or perhaps a proposed solution.
Right.
Its primary purpose isn't really to capture every single detail, but to reduce the inherent complexity, making an intricate system manageable and understandable.
That makes perfect sense. Trying to grasp an entire intricate system all at once is like attempting to see every single tree in a vast forest simultaneously.
You need a map, right? A simplified view to make sense of the landscape.
Exactly. A map is a great analogy.
So what's the real utility here? What problems do models solve for software engineers on the ground?
Well, the utility is multifaceted. First, they offer powerful visualization. They make it far easier to understand complex interactions and data flows that might otherwise be, impossible to grasp mentally.
Okay, seeing the connections. Yeah. Second, they aid in specification. They help teams make clear, unambiguous decisions by precisely defining components, their responsibilities, and their behaviors, nailing things down.
Uh-huh.
Third, models are crucial for construction. In more advanced forms, they can even serve as a foundation for what's called direct engineering, where portions of the code are actually generated directly from the model itself.
Wait, hang on. You mean a diagram literally becomes code? That sounds almost like magic.
Well, in certain specialized contexts, yes, it's a form of transformation from diagram to executable code. It's not everywhere, but it happens.
Wow.
Beyond that, models are invaluable for documentation. They serve as a living, evolving record of the system's design, which is crucial for maintenance.
A living record. I like that.
And in some highly specialized fields, they can even be used for simulation. Like with colored Petri nets, for example. You can use them to predict how a complex system will behave under various conditions before any implementation begins.
Okay, so this isn't just some academic exercise then. For our listeners, why does understanding this initial modeling step really matter to you, even if you're not writing code every day?
Because in a world where software systems are becoming exponentially more complex, models are truly the unsung heroes that make large-scale systems manageable. They prevent those systems from spiraling into unmanageable big balls of mud, as they're sometimes called.
Ah, the dreaded big ball of mud.
Exactly. But what's particularly powerful is their role as a common language. Imagine trying to build a skyscraper. If the architects, engineers, and construction crews all spoke different languages about the blueprints, it would be chaos.
Right.
Models bridge that communication gap between diverse teams, clients, business analysts, designers, developers, reducing ambiguity and streamlining the entire development process. They ensure everyone is literally on the same page.
And I gather there are different ways to draw these maps, different lenses to apply to the system. It's not a one-size-fits-all approach, is it?
No, definitely not. A model can emphasize functional aspects,
Yeah.
what the system does,
Okay.
or it could focus on structural aspects, how it's built.
The architecture.
Exactly. Or even behavioral aspects, detailing how it acts over time, how it responds to events. Each perspective provides unique, valuable insights into different facets of the system.
Let's zoom in on some specific types of models then. A foundational tool I know often used in earlier methodologies is the data flow diagram, or DFD. What's the core idea here?
Yeah, DFDs are a cornerstone tool within what's called structured systems analysis. They provide a high-level yet incredibly insightful view of a system, but specifically from the perspective of external entities and how they interact.
How data moves.
Exactly. The fundamental principle is to illustrate the flow of data through a system, where it comes from, where it goes, what processes transform it, and where it's stored.
So it's about seeing the system through the lens of data's journey rather than just, say, the classes or objects.
Precisely. And DFDs are typically created at different levels of detail to progressively unpack complexity. You might have a level 0 DFD, often called the context diagram.
The big picture.
Right, it provides an overall system context, showing the entire system as just a single process and its interactions with the outside world, the external entities.
Okay.
Then a level 1 DFD would unpack that central process into its major internal processes, revealing more granular data flows and data stores inside the system. This progressive decomposition really helps in understanding system complexity layer by layer, starting broad and then drilling down.
I've heard DFDs can even be surprisingly useful for things like threat modeling. How does visualizing data flow help with security?
Oh, that's a powerful practical application. By clearly visualizing every single pathway data takes through a system, you can immediately identify potential points of data exposure, maybe unauthorized access, or even manipulation.
You can see the weak spots.
Exactly. It's like an X-ray of your data's journey, highlighting vulnerabilities that might otherwise remain hidden within complex code. So yeah, it's an invaluable tool for security analysis.
Okay, moving from data flows to what feels like a more universal language in software, we have UML, the Unified Modeling Language. This really does sound like the Rosetta Stone for understanding software, covering many different perspectives.
UML is indeed a widely recognized and incredibly comprehensive standard. It offers a rich toolkit of diverse graphical representations, moving far beyond just data flows to capture various dimensions of a system's design. It's much broader than DFDs.
And there's a whole library of diagrams within UML. For our listeners who might not be building these themselves, what are some of the most essential or commonly encountered UML diagrams that truly help illustrate a system's design?
Well, UML is extensive, you're right. But for deeper understanding, let's maybe focus on 3 core types that are incredibly insightful.
Okay.
First, use case diagrams. They're often your starting point. They show who interacts with the system, those are the actors, and what they achieve, those are the use cases. They define the system's boundaries and its primary functionalities.
What the system does for users.
Exactly. Then you have class diagrams. These reveal the static structure, the foundational nouns of your system, representing classes and their relationships. Think of it like the framework of a building.
The building blocks.
Precisely. And crucially, sequence diagrams. These bring it all to life by showing how objects talk to each other over time. They detail the order of messages passed between them, like a choreography of system behavior.
How things actually happen step by step.
Exactly. Those 3 together, use case, class, and sequence, give you a really strong structural and behavioral understanding of a system.
So we can use these models in a couple of ways, building from them or building them from existing code, right?
Yes, those are the 2 primary engineering approaches. Direct engineering involves using models to discuss design alternatives, nail down specifications, and guide the work.
Right.
And this is where that exciting possibility of generating code directly from some diagrams comes into play, a true model-to-code transformation. It can streamline development and ensure the code matches the design.
That's the holy grail, isn't it? Code that writes itself.
Well, maybe not quite writes itself, but certainly helps automate parts of it.
And the flip side, reverse engineering, sounds like archaeology for software. Digging into old code.
It is, in a way. Reverse engineering involves converting existing code back into graphical representations like UML
And
diagrams.
why would you do that?
It's incredibly useful for understanding legacy systems where original documentation might be scarce or outdated, or simply to get a quick visual overview of a complex code base you didn't write.
Yeah.
However, it's important to note the trade-off. These reverse engineered diagrams might incur losses compared to original models. Some of the original design intent or higher-level abstractions can be lost in translation from code back to diagram. They reflect what is, not necessarily what was intended.
Got it. But models aren't just rigid blueprints, are they? Can they be more fluid too? Perhaps even sketches on a whiteboard?
Absolutely. While they can be detailed blueprints for formal specifications, they also serve as intermediate languages for automatic code generation, or quick sketches for discussions and rapid decision-making, or even just partial documentation for a specific tricky part.
So even in agile teams that maybe don't like heavy documentation.
Yes, even in agile approaches where strict documentation is often minimized, modeling is still inherently present. It might be less rigorous in its notation, maybe it only exists on a whiteboard for an hour,
Hmm.
but its main purpose remains, supporting focused discussions and informed decisions about parts of the project or code without necessarily aiming for a complete, exhaustive model. The flexibility allows the intensity and formality of modeling to be adapted precisely to a project's needs.
So what does this all mean for you, our listener? Why should you spend mental energy on DFDs, UML, and this whole concept of modeling?
Well, understanding these tools helps you appreciate the intentional design choices behind the software you use and build every day. It moves beyond just writing lines of code to truly engineering a system, making sure it's well thought out, designed for a reason, and inherently clear in its purpose.
Right.
This foundational understanding is crucial because it helps you identify why certain applications struggle with scalability, maybe, or how a seemingly simple change can ripple through an entire system, impacting performance or security. It gives you a language, a framework, to articulate complex software problems and solutions.
That's a fantastic transition because now we're going to move from those abstract blueprints to the actual building blocks,
Yeah.
how we assemble the software structure using classes and relationships. It's like moving from the architect's drawing board to the actual girders, beams, and rooms of a building.
Indeed. And the critical first step in assembling this structure is building what's called the conceptual model. This begins with the careful identification and extraction of core concepts directly from functional requirements, user stories, or maybe detailed use cases. It's about pulling out the things the system needs to understand and manage.
So we're essentially looking for the important nouns in all the project descriptions, right? The entities, the ideas, the objects the system needs to know about.
Exactly. The search for these concepts focuses on recurring nouns in descriptions and discussions. These often mirror terms from the business domain. They might represent data sources or destinations, or highlight artifacts with which users interact. It's about understanding the real-world entities and ideas that the software will be designed to manage.
And there's even a classic guide for this, isn't there? Abbott's heuristic from 1983. I love how some of these foundational ideas have stood the test of time in software engineering, still relevant.
Well, absolutely. Abbott's heuristic offers a remarkably valuable linguistic guide for this initial identification. It suggests that proper nouns often indicate individual objects.
Like dispatcher 1.
Right. Common nouns often suggest classes, like dispatcher in general. Action verbs can translate into operations or methods.
Like assigns or creates.
Exactly. Qualifying verbs might signal inheritance. Verbs of possession, like has a, point towards aggregation. And adjectives often represent attributes or properties. It's a powerful linguistic lens through which to begin forming your software model from natural language descriptions.
Once you've identified these concepts, you don't just jump straight into code, do you? You create something like a data dictionary first.
That's absolutely right. Once identified, these important concepts are meticulously described textually, forming a data dictionary. This formalizes their meaning, their attributes, any initial relationships.
So everyone agrees what a notification is.
Precisely. For instance, in a fictional emergency record system we might use as an example, you define a dispatcher as the official managing notifications and opening incidents, a notification as the initial report of an event, an agent as the field officer responsible for responding to notifications, and an incident as the dispatcher-generated record characterizing a notification, which can lead to various emergencies requiring specific public agency attention and resource allocation. This clarifies terms and relationships precisely before any coding begins. It avoids so much confusion.
And the graphical representation of these concepts really comes to life through classes, which are the fundamental building blocks of object-oriented software.
Exactly. Classes serve as the molds or the blueprints for which individual objects are instantiated, created at runtime. Their collective structure and collaboration define the software's expected behavior. Each class bundles together related data, often called attributes, and the methods or operations that act upon that data.
And within a class, there's this idea of visibility, right? Who gets to see or use what from outside the class, like public or private?
Yes, visibility controls access to a class's members, its attributes, and operations. This is crucial for encapsulation, a core principle we'll discuss more later. It ensures that internal details are hidden and interactions occur only through defined public interfaces.
Keeps things tidy.
Very much so.
Okay.
We also have a simpler connection, sometimes called dependence, between classes, which isn't really due to association or inheritance in the formal sense. It typically indicates that one class simply needs another to perform a specific operation, perhaps using it as a temporary tool without storing it as a permanent attribute, a fleeting need, if you will.
Okay, so classes are these versatile molds. But
Yep.
then there are specialized types of classes that add even more clarity to the design. One that caught my eye was the association class. That sounds like a bit of a paradox, being both a class and a relationship at the same time.
It can seem that way, yeah.
Yeah.
An association class is a unique construct that is simultaneously a class and an association between two other classes. It's used when the relationship itself has attributes or operations that need to be modeled.
Can you give an example?
Sure. If a student enrolls in a course, and that enrollment itself has an attribute like grade or enrollment date, you might model enrollment as an association class linked to both student and course.
Ah, okay. The link itself has data.
Exactly. However, for actual coding, these often simplify to more traditional classes and simple associations, maybe an enrollment class with references to student and course, just to avoid unnecessary complexity in the implementation language. It's more a modeling concept.
Interesting. And then we have what's often called the triad of classes, entity, control, and boundary classes. Using these stereotypes, this really helps organize things, doesn't it, and keep different concerns separate.
This separation is absolutely fundamental for a well-structured system, especially in object-oriented design. Let's break them down. Entity classes represent the core domain concepts.
The main things.
Right. Think emergency reports or field officer in our example.
Mm-hmm.
These are the most stable and crucial for the product's vision because they model the real-world business concepts and data. It's vital here to resist the temptation to prematurely include technical solution classes, like UI elements, because that pollutes the model and can compromise its clarity and stability. Keep it focused on the business domain.
So entity classes are the pure, unadulterated business concepts and data. What about boundary classes, then? Where do they fit?
Boundary classes act as intermediaries. They sit at the edge of the system, mediating interactions between users, whether human users interacting with an interface or other software systems calling an API and the system's internal functionalities.
So the screens, the buttons, the API endpoint?
Exactly. Examples include buttons, forms, input fields, messages displayed to the user, or API gateways. Their primary role is to handle user input and present output, translating between the user's world and the system's world.
And then the control classes are the ones that actually make things happen, the traffic cops of the system,
Right.
coordinating the actions based on input from the boundary.
Precisely. Control classes have no direct real-world representation. Their entire job is to articulate the actions for specific functionalities, managing the flow, communication, and instances within the system. They gather information from boundary objects, coordinate with entity objects to perform business logic, fetch data, update things, and then dispatch tasks.
And you usually have one for each main feature or use case.
Typically, yeah. There's usually at least one control class per exposed functionality, and its lifecycle is tied directly to that functionality it comes into being when a specific task is initiated, like create an emergency report, and often fades away when the task is complete.
So why go through all this trouble? Why is this clear separation, entity, boundary control so important for a system's health? It sounds like extra work.
It might seem like it initially, but this separation promotes significant long-term benefits. It dramatically increases code cohesion within each type of class, meaning elements within a class are highly related and serve a single purpose.
Makes sense.
It simplifies maintenance because changes are localized. If the UI changes, you mostly change boundary classes. If a business rule changes, you look at control or entity classes.
Less ripple effect.
Exactly. And crucially, it reduces coupling unnecessary dependencies between different parts of the system. Boundary interfaces and business rules and control classes tend to change more frequently than the core domain structures represented by entity classes. By isolating these concerns, changes in one area have less impact on others, making the system far more adaptable and robust over time. It pays off handsomely.
Now, once we have these classes, they rarely exist in isolation, right? Software isn't just a collection of independent boxes. This is where relationships come in, defining how they interact. And the most fundamental one seems to be association. It's basically the knows-er relationship.
That's correct. Association is a structural relationship indicating that objects of one class are connected to objects of another for some period of time. It's the most generic relationship and implies that one object holds a reference to another, typically as an instance attribute, allowing it to call that object's methods or access its public data. Think of it as a line connecting classes on a diagram.
So if a field officer writes an emergency report, that's an association. Simple enough. But how many reports can an officer write, and how many officers write a report? That's where multiplicity comes in, isn't it, to define the rules of these connections?
Yes, multiplicity is absolutely crucial for expressing the business rules of the domain directly within the model. It's indicated at the ends of the association line, often with numbers or symbols like Ellie. It specifies the number of possible instances related to each object of the class at the other end.
Give me an example.
Okay, so a field officer writes 0 to many emergency reports, meaning an officer might write none, 1, or many reports. While an emergency report is always written by exactly one field officer. That's a business rule captured right there. Multiplicity can also represent more complex scenarios, such as an emergency notification can be written by a minimum of 1 and a maximum of 1.2 field officers.
Captures the rules precisely. And sometimes an association needs a specific name or label to clarify its meaning beyond just the two classes involved, right?
Absolutely. The label or name of an association identifies the relationship when its meaning isn't immediately obvious from the classes themselves. For instance, between student and course, an association might be labeled matriculated in.
Much clearer than just a line.
Exactly. This clarifies the specific nature of the connection. Complementary to the label, each class often plays a specific role in the association, like student playing the role of learner and course playing the role of educational offering in that example. These details are vital for clear semantic understanding.
And you mentioned avoiding unnecessary associations.
Yeah, it's also good practice to avoid unnecessary associations that just clutter the model and make it harder to understand. For instance, if an incident is linked to an emergency report and the emergency report is linked to a field officer, you probably don't need a direct link from incident to field officer unless there's a very specific reason. Keep it clean.
Makes sense. Moving beyond simple associations, we have the whole part relationships, aggregation and composition. What's the subtle but important difference between has and is part of? They sound similar.
They do sound similar, but the distinction is about life cycle and independence. Aggregation, represented by a white diamond symbol in UML, signifies a has a relationship where the parts can exist independently of the whole.
Okay,
Think of a player in a team. A player can exist even if the team is disbanded, right?
Mm-hmm.
And a player might even be part of multiple teams over their career. The part's life cycle is not strictly dependent on the whole.
Got it. The player object doesn't get deleted if the team object does.
Exactly. But composition, shown with a filled black diamond, is much stronger. It implies is exclusively part of, and critically, a shared life cycle.
So if the whole goes, the part goes too.
Precisely. Here, the parts are intrinsically tied to the whole. If the whole is eliminated, the parts are too, at least in that specific context. A classic example is a vehicle and its engine. If the vehicle is scrapped, that engine, as part of that vehicle, also ceases to exist in that context. Its life cycle is bound to the whole.
That's a clear difference.
It is. But a practical guideline is, if you're ever in doubt about the strict whole part semantics or whether the part can truly exist independently, it's often best to just use a common association. It's the most general and flexible and avoids potential misinterpretations of aggregation versus composition, which can be subtle.
Good advice. Then there's what often feels like the weakest link in relationships. Dependency, shown with the dashed arrow. That's the uses a relationship you said.
Yeah, dependency indicates that one class, the client, needs another class, the supplier, to perform a specific operation. But crucially, it doesn't store that supplier as a permanent instance attribute. It's a transient, temporary relationship.
So it uses it briefly, then forgets about it.
Kind of. This often occurs when a class is used as a method parameter, maybe a local variable type inside a method, or a return type. For example, a report generator might depend on a database connection only for the duration of a single report generation method call, not stored as a permanent field.
But if I change the supplier class, the database connection in that example, the client class, the report generator, might still break, even if it doesn't own an instance of it. That's a crucial kind of coupling to be aware of, even if it's temporary.
Exactly. It implies a temporary need, not a lasting structural connection like association, but changes in the supplier can indeed still ripple and break the client. It's a lighter form of coupling, but coupling nonetheless.
And that leads us to a fundamental debate in software design, the ISA versus has-A discussion, which brings us to inheritance, or generalization in UML terms, shown with the hollow triangle.
Right. And this one often trips people up, as you said. Inheritance is fundamentally not an association. It's about code reuse and specialization, where a subclass inherits or reuses specifications, attributes, and behaviors from a superclass.
So in code, it doesn't create a link between two separate objects like an association does. It defines the structure of the subclass object itself.
That's a crucial distinction. It's about a subclass being a kind of its superclass, gaining its attributes and/or behavior. Now, a fundamental design principle, often summarized as prefer composition to inheritance or favor has a delegation over ISA extension, aims to achieve better design qualities.
Why is that preferred?
Because using composition, where one object holds a reference to another, HASA, and delegates tasks to it, often leads to higher cohesion, greater extensibility, and critically lower coupling compared to inheritance, ISA. This approach frequently allows parts to be changed or extended without impacting other parts of the code as drastically. Inheritance can create very tight, brittle coupling.
And this prefer composition idea is tightly coupled with one of the famous solid principles, isn't it? The Liskov substitution principle, LSP.
It is, very tightly. LSP, named after Barbara Liskov, states, if S is a subtype of T, then objects of type T may be replaced with objects of type S without altering any of the desirable properties of that program.
Okay, unpack that a bit.
In simpler terms, a subclass must be truly substitutable for its superclass without breaking functionality or violating any assumptions clients make about the superclass. If you substitute a subclass instance where a superclass instance is expected, everything should still work correctly. This is absolutely critical for building robust and predictable inheritance hierarchies. Otherwise, you introduce subtle, unexpected bugs.
So, if a square class inherits from a rectangle class, that seems intuitive, right? A square IS, a rectangle.
It seems intuitive, but it's a classic example where LSP can be violated.
How?
Well, a rectangle might have separate setWidth and setHeight methods. If a square inherits these, what happens if you call setWidth 5, then setHeight on a square object? To maintain its squareness, the square might have to override these methods to change both dimensions together, or throw an error. But a client using a rectangle variable wouldn't expect setting the height to also change the width.
Ah, it breaks the expected behavior of the rectangle.
Exactly. The square subclass alters fundamental assumptions about the rectangle superclass's behavior, leading to unexpected outcomes for clients using the superclass type. It violates LSP. Often, using composition here, having a square contain a single side-length attribute is a much cleaner design.
That makes sense. So what if two classes have multiple ways of relating? Can they have more than one association between them?
Yes, absolutely. Two classes can have multiple distinct semantic relationships between them. Each one is treated as an independent association on the diagram, complete with its own multiplicity, its own label, and its own roles if needed.
Like?
For example, an employee and a project could have both a works-on association, maybe many-to-many, and a supervises association, maybe one-to-many from employee to project. Each distinct relationship will then translate into a separate attribute or collection of attributes in the code of one or both classes, referencing instances of the other class.
And that leads us to navigability. The little arrows you sometimes see on association lines, that defines which class knows about the other, guiding the creation of those attributes, right?
Correct. Navigability, indicated by an arrow, shows which class will possess an attribute that references instances of the other class in an association. It guides the direction of knowledge or awareness between them. If there's an arrow from Class A to Class B, it means Class A instances hold references to Class B instances.
And sometimes it goes both ways.
Yeah, sometimes navigation can be bidirectional, meaning both classes know about each other and hold references. We also have what are sometimes called association of attributes, things like one-to-one or one-to-many relationships, which impact how references are maintained in the code for efficiency, especially for quick retrieval and avoiding redundant data storage.
Okay, so we've got classes, And we've got how they relate to each other. But how else do software engineers organize their creations beyond just individual classes? Are there larger containers for managing complexity, especially in huge systems?
Yes, absolutely. There are other classifiers that help organize model elements at a higher level, which become crucial for managing the complexity of large systems. Packages are a common one. Think of them like logical folders in your file system, used for grouping related classes, diagrams, or even other packages. They help structure the model itself.
Keeps the model tidy.
Exactly. Then you have components. These represent cohesive functional blocks with clearly defined interfaces for exposing services they provide and requiring services they need from others. They're more about the runtime structure.
Like reusable modules.
Kind of, yeah. And deployment diagrams are specialized UML diagrams. They show how these software components are distributed and run across physical hardware nodes or virtual environments. Where does the code actually live and execute?
So, understanding how these larger components communicate through their interfaces is vital for system architecture, too. That interface is the contract, right?
It is. The interface defines the contract for how components communicate without needing to know each other's internal complexities or implementation details. It's the public face of a component's capabilities, what it promises to do.
Why should our listeners care about these packages, components, and deployment diagrams? What's the practical takeaway?
Well, understanding these organizational tools is fundamental to reading and designing robust software architectures. It's about appreciating how the building blocks fit together and interact on a larger scale, laying the groundwork for scalable, maintainable systems.
So, it's not just code, it's the whole structure.
Right. When you encounter a slow or fragile application, often the root cause lies not just in a single buggy line of code, but in poorly organized components, tangled dependencies, or unclear interfaces between them. This knowledge helps you diagnose architectural health, not just code quality. It helps you think about the system level.
That's a perfect lead into our next segment because once you have your blueprints and your building blocks, you need a set of guiding principles and proving patterns to ensure you're building quality software. This isn't just about making it work, it's about making it work well and for a long time. It's the difference between a functional shack and a resilient, adaptable skyscraper.
Indeed. The quest for better code revolves around key goals, particularly for reuse, achieving greater cohesion within modules, making sure they do one thing well, increasing extensibility, making it easy to add new features later, and crucially, reducing coupling or unnecessary dependencies between different parts of the code. These are really the pillars of maintainable software.
And one of the ways to achieve these goals, which we touched on earlier when discussing inheritance, is delegation, often used as a powerful alternative to direct inheritance.
Delegation truly emerges as a more flexible and robust alternative to inheritance in many, many scenarios. Instead of an ISA relationship, which inheritance implies, delegation uses a has-a relationship implemented through composition by integrating another class to reuse its code. One object holds a reference to another and forwards requests to it.
And why is that often better?
This approach is often more advantageous for promoting reuse and extensibility and critically reducing coupling. It also allows behavior to be modified potentially at runtime, which inheritance usually doesn't.
You know, I remember you mentioning the MySet as hash table example in a past discussion. That perfectly illustrates how powerful delegation can be compared to naive inheritance, especially when thinking about the Liskov substitution principle we just covered. Could you quickly remind us of that?
Certainly. If you tried to create a MySet class by directly inheriting from a hash table, maybe because a set can be implemented using a hash table internally.
Seems logical at first glance.
Right, but then if you overrode a method, say clear, to maybe do nothing or throw an error, because conceptually, clearing a set might not make sense in the same way as clearing a hash table, or you want different semantics, you could easily violate the Liskov substitution principle.
How so?
A client holding a variable of type hash table might call clear on what is actually a MySet object, and be very surprised when it doesn't behave as a standard hash table's clear method would. It breaks the contract.
Right, unexpected behavior.
By contrast, if MySet delegates to an internal hash table instance, a has-a relationship, MySet controls exactly how its elements are managed, ensuring its behavior is consistent with set semantics, while still leveraging the hash table's efficient storage and lookup capabilities safely and cleanly behind the scenes. This preserves the integrity of the base class concept while still reusing its functionalities safely.
That's much cleaner. Here's where it gets really interesting for practical application. Let's think about this with a concrete example, like designing game characters and their behaviors. Imagine you're building a game with different characters. A wizard, a warrior, a healer. They all have basic actions like moving, maybe talking. Now, you decide you want your wizard character to be able to fly.
Okay. The initial, perhaps intuitive thought might be, okay, easy, let's just add a fly method to the base character class that wizard, warrior, etc. inherit from.
But immediately you hit a problem, right? Because not all characters fly. Your warrior doesn't fly. Your healer might not fly. Maybe you have adult or child characters that definitely don't fly. You'd end up with empty implementations or irrelevant methods in many classes, which is confusing and brittle, makes the base class messy.
Exactly. So another attempt might be to define a default, maybe empty or null fly method in the base class, and then override it, implement this specific flying behavior only in the wizard class.
But again, that's not ideal because if the core flying behavior ever needs to change, say, you introduce a new flying mechanism like magical wings versus a jetpack, or you refine the physics you'd potentially have to modify many different character classes that implement flying, that becomes a maintenance nightmare, especially in a large game with dozens or hundreds of character types.
Yeah, that scales poorly. You might then consider specialized interfaces, perhaps.
Oh.
Only characters that fly implement a flyable interface.
That sounds better.
It's better for type safety, maybe. But it can still lead to code replication if, say, a mage and maybe a flying monster both implement flyable but fly in a very similar way. You might duplicate that flying logic. It can also create polymorphic issues if you try to treat all characters uniformly, but only some are flyable. Plus, you typically can't easily change their flying behavior at runtime. A wizard can't suddenly switch to using a jetpack if they lose their magic.
So how do we solve this elegantly? This is where encapsulating variation with design patterns comes in, right? It's about cleverly separating the aspects that might change, like how something flies, from those that are stable, like the core character concept.
The core idea here, and it's a cornerstone of good object-oriented design, is to program to interfaces, not implementations, or sometimes phrased as program to abstractions. This is precisely where design patterns become invaluable tools. They offer proven, well-documented ways to achieve this separation, making your code flexible, reusable, and robust.
So how would this work for our flying wizard using something like the strategy pattern?
Okay, with the strategy pattern, your base character class wouldn't have a fly method directly. Instead, it would define a generic behavior attribute. Let's call it fly behavior. And the type of this attribute wouldn't be a concrete flying implementation, but an interface, say, I fly behavior.
An interface defining a fly method.
Exactly. Then, concrete methods in the abstract character class, like maybe a perform fly method, would perform the behavior simply by delegating the call to whatever object is currently held in the fly behavior attribute. So, flyBehavior.fly.
It just passes the buck.
Pretty much.
Yeah.
The specific flying behaviors, say, knowings flying, magic flying, jetpack flying, are implemented in separate classes, each of which implements the iFly behavior interface.
And the magic is that you can assign these behavior objects to your characters based on their configuration, maybe in the constructor, or even change them at runtime. So a wizard could temporarily lose their magic, and you could set their fly behavior to knowings flying if needed without altering the wizard class itself.
That's incredibly powerful for adaptability. Precisely. This analytical approach, leveraging delegation, character has fly behavior, and interfaces, is much more suitable. It allows for behavior modification at runtime and truly encapsulates the varying aspect of flying from the stable character definition. This results in a system that is far more flexible, maintainable, and adheres to principles like open-closed.
That's a great illustration. The big takeaway here, again, is that has A, delegation or composition, often trumps Is A, inheritance or extension, for achieving greater reuse, extensibility, and crucially, reduced coupling.
Yeah, it's a really fundamental design choice.
And this leads us directly to the concept of design patterns themselves. They're not just clever tricks you invent on the spot. They are documented, reproducible solutions to recurring software development problems. Think of them as best practices distilled from experience into formal, reusable patterns that provide a common vocabulary for developers. Saves reinventing the wheel.
Exactly. And having that common vocabulary is huge for team communication. Every well-documented pattern typically has 4 fundamental elements that help in understanding and applying them effectively.
Okay, what are those?
First, a unique name, like strategy or observer, for easy communication. Second, a clear description of the problem it solves, detailing the specific situation or context where the pattern applies, along with the forces or trade-offs that compel its use.
When should I even think about using this?
Right. Third, the solution, presented often in terms of classes, interfaces, collaborations, and high-level representations of how the problem is solved structurally and behaviorally.
A pattern itself.
Yeah, the core structure. And finally, the consequences, which outline the pros, cons, and trade-offs of applying that particular pattern. Understanding these trade-offs is crucial because no pattern is perfect for every situation.
Okay, let's quickly reiterate the strategy pattern as our first example, based on what we just discussed.
Right. The strategy pattern encapsulates a family of algorithms, like different ways to fly or sort or validate, making them interchangeable. It allows the client, like the character class, to choose or be assigned an algorithm at runtime, directly addressing our game character flying example, where different flying mechanisms could be swapped in and out without altering the core character logic, decouples the how from the what.
Perfect. Then we have the observer pattern. This one sounds like it's all about staying informed, especially when one part of the system needs to react automatically to changes in another part without them being tightly coupled.
That's exactly the problem the observer pattern solves. Maintaining consistent updates between objects when one object, the subject, changes its state. It defines a one-to-many dependency relationship. A single subject object automatically notifies multiple dependent observer objects when its state changes, usually by calling an update method on each observer.
Where would you use that?
It's widely applied in interactive systems, graphical user interfaces, and event handling systems. Think about a spreadsheet when you change a cell value, the subject. All the formulas or charts, the observers that depend on that cell, need to update automatically. MVC architectures often use it heavily, where multiple views, observers, need to reflect changes in the same underlying model, subject, without the model needing to know about specific views.
What are the benefits?
Its key benefit is that it removes direct dependence between the subject and its observers. The subject only knows it has a list of observers conforming to an interface. This contributes significantly to the open-close principle. You can add new observers without modifying the subject. And the dependency inversion principle. Both subject and observer depend on an abstraction.
Very flexible. And finally, let's touch on the singleton pattern. This sounds like it's about enforcing uniqueness, making sure you only ever have one instance of something no matter what. The Highlander pattern there can be only one.
Exactly. The singleton pattern's primary goal is indeed to ensure that a class has only one instance throughout the application's lifecycle, and it provides a single global point of access to that instance.
Why would you want only one?
This is crucial for managing access to shared resources or services, where having multiple instances could lead to inconsistencies, resource waste, or race conditions. Think about things like database connection pools, application-wide configuration managers, logging services, maybe hardware device drivers. You really only want one central point controlling those.
So how do you even implement a singleton technically to guarantee that uniqueness and control access? It sounds tricky.
To implement a singleton robustly, you typically take several steps. First, you declare the class itself, often as final, in languages like Java or C# to prevent subclasses from potentially messing up the singleton guarantee.
Okay.
Crucially, its constructor is made private. This prevents any external code from just creating new instances using new...
Locks it down.
Right. Then, a private static attribute within the class itself holds the single instance. It might be created eagerly when the class loads, or lazily when first requested.
So the class holds its own single copy.
Exactly. And finally, a public static method, conventionally named getInstance, provides the global access point. This method returns the single instance, creating it only if it doesn't already exist in the lazy initialization case.
And what about threads? If multiple parts of the code call getInstance at the same time.
Good point. For robustness in multi-threaded environments, the getInstance method often incorporates a synchronized mechanism or uses more advanced patterns like a lazy initialization halter class or double-checked locking, though that can be tricky, to ensure thread-safe creation, preventing multiple instances from being accidentally created under concurrent access.
Okay, so these patterns are powerful, but they're built on even more fundamental concepts, the core project properties that guide good design in general. These are the bedrock principles, you call them.
These properties are truly the bedrock. They are fundamental guidelines, almost like quality attributes for building robust, maintainable, and extensible systems. The four key ones we often discuss are conceptual integrity, information hiding, cohesion, and coupling. Mastering these is key to creating systems that last and don't become nightmares to work with.
Let's start with conceptual integrity. That sounds like keeping everything consistent and making sense together from the overall vision down to the tiny details.
Exactly. Conceptual integrity refers to the coherence and consistency of a system's functionalities, its design choices, and its user experience. It prevents a system from feeling like a pile of disconnected features or an inconsistent mess. It ensures that similar elements behave and are represented uniformly throughout the system.
Like using the same icon for save everywhere.
That's a UI example, yes. But it also applies to the code. Consistent naming conventions across the code base, using the same version of a framework consistently, applying appropriate data structures uniformly for similar problems. Its core benefit is a system that is easier to use and understand for both end users and, crucially, for developers maintaining the code. Good component decomposition, which we'll discuss later, often helps maintain this integrity by assigning clear, consistent responsibilities.
Then there's information hiding, also known as encapsulation. This is about keeping secrets, isn't it? Hiding the inner workings of a module or class.
Yes, in a way. Information hiding dictates that classes or modules should conceal their internal implementation details, especially those details that are prone to change over time. The core idea is that a class should present a stable, public interface, its contract, so that internal modifications or refactoring don't break external clients using it.
Can you give an example of bad information hiding?
Sure. Imagine a parking lot class that internally uses a hash table to store cars. If it exposes that hash table directly via a public getInternal table method, allowing external code to directly manipulate the table, that compromises its independence and flexibility. If the parking lot later wants to switch to a different internal data structure, like a tree map, it will break all the clients that were directly accessing the old hash table. Bad design.
Got it. Hides the mess inside.
Exactly. This property directly fosters componentization by hiding internal complexity, making modules truly more like black boxes or plug-and-play units.
And cohesion. That's about how tightly related things are within a single module or class, ensuring it has a single, clear purpose.
Cohesion describes the degree to which elements within a module belong together functionally. A highly cohesive module has a single, well-defined purpose or offers a single, focused type of service.
What's an example of low cohesion?
A common counterexample is a class that both calculates, say, a student dropout index, and also handles formatting and printing that index to a specific report file. Those are two distinct responsibilities, calculation and presentation output. They should likely be in separate classes or modules.
And high cohesion.
A good example is a stack class with methods like push, pop, peek, and isEmptyAll, serving a common purpose directly related to managing the stack data structure itself. High cohesion simplifies maintenance because changes related to one specific responsibility are localized to that single, focused module. It makes code easier to understand and modify.
And the flip side of that, often seen as its natural enemy, is coupling. This is about how much different parts of the software depend on each other, right? The connections between modules.
Exactly. Coupling describes the degree of interdependence between different software units, like classes or modules. While some level of dependency is obviously unavoidable for modules to collaborate, the primary goal of good design is to minimize unnecessary coupling, especially dependence on unstable or internal implementation details. We prefer dependencies on stable, well-defined interfaces.
What's an example of bad, tight coupling?
Bad coupling occurs when one class depends heavily on the internal implementation details of another, not just its public interface. Or when the dependence isn't via an interface at all, like one class directly reading a file that it knows is saved in a specific format by another class without that other class's explicit knowledge or contract.
Why is high coupling bad?
High coupling means changes in one part of the system can have a cascading, often unpredictable impact on many other parts throughout the system. It creates ripples. Debugging becomes harder, maintenance is riskier, and reuse is hindered. Promoting decoupling, minimizing these dependencies, is a central objective of good design and the reason behind many design patterns like Observer and even architectural styles like microservices, which aim to isolate changes and allow independent variation.
Speaking of core principles, we absolutely have to talk about SOLID. These 5 fundamental principles are like the bedrock of modern object-oriented design, guiding engineers toward creating software that is understandable, developable, and maintainable over its entire lifecycle. They seem to come up everywhere.
They truly are foundational, often attributed to Robert C. Martin. They represent distilled wisdom for OAO design. Let's break them down quickly. First, the S stands for the Single Responsibility Principle, SRP.
We touched on this with cohesion. A class should have only one reason to change.
Exactly. If a class is responsible for both business logic calculations and database persistence, it has two reasons to change if the calculation rules change or if the database schema changes. SRP says split those responsibilities into separate classes.
Makes sense. Increased cohesion, simpler maintenance.
Precisely. A business logic class, for example, can then be reused by various interface classes, web UI, mobile UI, batch process, without becoming coupled to their specific display or persistence concerns.
Okay, next is O, the open-closed principle, OCP. This one is key. Open for extension, but closed for modification. It sounds almost contradictory.
It does, but it's incredibly powerful. OCP means that the behavior of a software entity, like a class, module, or function, should be extendable. You should be able to add new functionality without altering its existing working source code.
How do you achieve that? Magic.
Not quite magic. It's typically achieved through mechanisms like abstraction using inheritance, implementing interfaces, or using composition with dependency injection. Think back to our strategy pattern example. The character class was closed for modification. We didn't change its code to add new flying types, but it was open for extension because we could create new classes implementing the iFly behavior interface and plug them in.
Using polymorphism and abstraction.
Exactly. Another example, if you have a sorting algorithm, it should be open to sorting a list of, say, strings by length, maybe by accepting a client-implemented comparator object, without the core sorting logic needing to be rewritten every time a new sorting criterion emerges. The core sorting code remains closed.
Very cool. What's L?
L is the Liskov substitution principle, LSP, which we discussed earlier with inheritance.
Right, subtypes must be substitutable for their base types without breaking things. The square rectangle problem.
Exactly. It ensures that inheritance is used safely and correctly, maintaining behavioral consistency.
Okay, I is for...
IA stands for the Interface Segregation Principle, ISP. This sounds like it's about making sure interfaces aren't too big or fat, forcing clients to depend on methods they don't actually use.
Like a Swiss Army knife interface with too many tools?
Kind of. ISP is essentially SRP applied specifically to interfaces. It dictates that clients should not be forced to depend on interfaces they don't use. Interfaces should be small, cohesive, and client-specific. Instead of one massive employee interface with dozens of methods for payroll, time tracking, performance reviews, benefits, etc., you'd likely have smaller, more focused interfaces like payable, time trackable, reviewable. A part-time contractor class might only implement payable and time trackable, not reviewable, thus avoiding a dependency on methods it doesn't need. This reduces unnecessary coupling.
Makes interfaces cleaner and more focused. And finally, D.
D is the dependency inversion principle, DIP, often summarized as depend upon abstractions, not concretions, or prefer interfaces to classes. This seems to be at the heart of flexible decoupled systems.
How does that work?
DIP suggests that high-level modules, or actually business logic, should not depend directly on low-level modules, right? Everything's database access code, specific UI widgets. Instead, both should depend on abstractions, like interfaces or abstract classes defined by the high-level module.
So the business logic defines the interface it needs, and the low-level module implements that interface.
Exactly. This inverts the traditional dependency flow where high-level depends on low-level. This significantly reduces coupling and makes it much easier to substitute concrete implementations. It's the very basis for techniques like dependency injection and allows systems to be much more pluggable and testable. It's fundamental to the strategy and observer patterns we discussed, where the high-level class depends on a behavior interface, not a concrete behavior class.
We also briefly mentioned the principle of Demeter, or law of Demeter. That was the one about not talking to strangers, or rather, friends of friends.
Right. It's often phrased as a method should only talk to its immediate friends, not the friends of its friends. It advises against long chains of method calls like obj.getty b.getty something.
Why are those chains bad? They seem convenient sometimes.
They seem convenient, but they deeply compromise encapsulation by exposing too much about the internal structure of intermediate objects, A and B in that chain. They also add intellectual overhead, you need to know the whole chain, and processing overhead. More importantly, they make the code incredibly fragile. If the structure of object A or B changes, your calling code breaks, even if C's interface hasn't changed. The goal is to reduce these dependencies and preserve encapsulation by limiting the scope of knowledge talk only to objects directly passed in or created locally or held as instance variables.
Okay, so why do all these principles, solid and the others like Demeter, truly matter? They sound like, nice academic ideals that might only benefit a theoretical computer science paper. Do they really help in practice?
Oh, absolutely. They might sound abstract, but they are battle-tested guidelines refined over decades of software development experience. Adhering to them leads to software that is fundamentally easier to manage, adapt, and evolve over its lifetime. This saves countless hours, reduces stress, and lowers costs in the long run.
How so? Tangible benefits.
Definitely. They translate directly into tangible benefits like reduced bugs, because code is clearer and changes are localized, faster development cycles, because new features can be added more easily without breaking existing ones, easier testing due to decoupling, and generally happier development teams who get to work with a clean, understandable, flexible code base instead of a tangled mess. When a system built with these principles encounters a new requirement or needs a change, it tends to flex and adapt gracefully rather than breaking in unexpected ways. They are intensely practical.
Now that we've covered the blueprints, the building blocks, and the guiding principles, it's time to talk about how we actually put it all together. Implementing those functional requirements and choosing the right architectural style for the system. This is where the rubber meets the road, translating all that conceptual design into actual executable code that delivers what users need.
This stage truly is the bridge, as you say. It's about transforming the conceptual model. All those elegant ideas about classes, relationships, entities, controls we just discussed, into the actual architecture and the code that will deliver the user's functionalities. It involves seeing how abstract conceptual elements from requirements or use cases are concretely supported by technical elements, like specific components or services in the solution domain.
And to visualize how all these pieces interact dynamically at runtime, especially how messages are passed between objects to fulfill a use case, we often use sequence diagrams, right? They're like storyboards for how objects talk to each other in a specific scenario.
Exactly. Sequence diagrams detail the behavior of a use case or a specific scenario, showing the communication flow between objects, represented by vertical lifelines, and actors over time. Time flows down the page. They bring the dynamic aspect of the system to life, illustrating method calls, message exchanges, synchronous or asynchronous, and the order in which operations occur. They're invaluable for understanding and verifying runtime behavior.
So how do you even begin to create one of these? Are there common heuristics or rules of thumb for mapping interactions, especially linking back to those entity boundary control classes?
There are. A common heuristic, especially when following that EBC pattern, suggests a natural progression across the columns, lifelines, in your diagram. The first column, the initiator, should typically represent the interacting entity that starts the functionality, often an actor, like a user clicking a button, or maybe an external system trigger.
Okay, the start of the flow.
Yeah. The second column is usually a boundary object like the UI screen or the API endpoint that receives the initial request.
A gatekeeper.
Right. The third column then becomes the control object associated with that use case, which manages the core functionality orchestrating the interaction. This control object then calls methods on various entity objects, which appear further to the right, to retrieve data, update state, or perform business logic.
So actor, boundary, control, entity.
That's a very common and effective pattern. Entity objects are accessed by control objects and sometimes directly by boundary objects if it's just simple data display.
And there's a crucial rule here, isn't there? One that really reinforces good design principles we just talked about, like low coupling and high cohesion, especially regarding entities.
Yes, a critical rule, particularly for achieving low coupling and high cohesion and keeping your domain model pure, is that entity objects should never directly access or call methods on boundary or control objects. This is paramount.
Why is that so important?
Your core business data objects, entities, should remain completely insulated from specific UI concerns, boundary, or workflow management logic, control. They should just represent the data and its intrinsic rules. This promotes reuse and stability, because your fundamental business entities don't need to change if the user interface changes or the workflow for a use case is altered. They remain independent.
Okay, so why is mapping out this sequence of interactions and sticking to rules like that so important for a system's health overall?
It helps ensure that the system's actual runtime behavior aligns precisely with the intended design. By visualizing the message flow, you can catch potential logic flaws early, identify inefficient communication patterns, like maybe too much back and forth chatting between objects, or spot design inconsistencies before you write a lot of code. It's a powerful tool for validating the dynamic aspects of your architecture and ensuring it performs as expected.
Now, when systems get big and complex, you can't just have one giant blob of code, even if it uses classes nicely. You need to break it down into bigger chunks. This is where component decomposition comes in, right? Structuring the system at a higher level.
Absolutely. Component decomposition is a fundamental architectural approach that segments the software into cohesive functional blocks. These blocks can be called components, layers, packages, subsystems, or, in more modern architectures, microservices. The core goal is always the same. Manage complexity by breaking a large, overwhelming problem into smaller, more manageable, understandable pieces.
And this involves more than just splitting code files randomly. It's about identifying dependencies carefully and defining precisely how these larger pieces talk to each other, isn't it?
Precisely. Key aspects include identifying the precise dependencies between these blocks, which component needs services from which other component, specifying the clear interfaces each component exposes, what it offers, and requires, what it needs, potentially mapping components to the hardware or virtual environments where they'll execute deployment, and defining how data will persist and be accessed by these components, perhaps through dedicated data access component.
What are the big practical advantages of breaking things down this way? Why go through the effort of defining components and interfaces?
The advantages are numerous and significant, especially for large or long-lived systems. It drastically reduces overall system complexity by enabling independent development, testing, and understanding of each part.
Divide and conquer.
Exactly. It promotes reuse of components across different parts of the system or even different projects. It makes component substitution easier. You can swap out an old component for a new, improved one without affecting the whole system if the interface remains stable. This significantly improves overall system maintenance and evolution.
Easier to upgrade parts.
Right. It also standardizes how services are exposed and dependencies are described, making the architecture more explicit. And where feasible, it enables parallel development across different teams working on different components, potentially accelerating delivery timelines.
You mentioned managing dependencies being key. Could you give an example of how componentization specifically helps with that, perhaps with something common like database integration?
Sure. Consider integrating a database. If all your application components, like order processing, inventory management, user profiles, directly use the database's raw interface, example specific SQL queries or a particular database driver API.
Which might seem simplest at first.
Right, but any change to that database technology or its schema, or even deciding to replace it entirely with a different database, would necessitate potentially complex modifications across all those consuming application components. That's tight coupling to the database implementation.
A maintenance nightmare.
Totally. The elegant solution, leveraging componentization, is to create an intermediate component, often called a data access layer or repository component. This layer encapsulates all communication with a storage subsystem, the database. It exposes a stable, high-level service interface, example, get user by ID, save order, to the other application components.
So the other components talk to this layer, not the database directly.
Exactly. This effectively reduces coupling, isolating the other components from direct changes to the database implementation. They depend on the stable data access interface, not the volatile concrete database details. You can swap the database behind that interface, and ideally the other components don't even notice.
That's a huge win. And within these components, we talk about services, right? What exactly is a service in this architectural context, and how does it relate to a component?
A service is essentially a defined set of related operations that grants access to the functionalities offered by a component. Think of it as a coherent capability exposed by the component. These services are exposed to other components via well-defined public interfaces. A single component can, in fact, expose multiple distinct services through different interfaces, reflecting various ways it can be consumed or depended upon. But critically, these interfaces are the only ways other components should interact with it, respecting its encapsulation.
This leads us naturally to architectural paradigms or styles, the big picture patterns for structuring entire systems. These are like common blueprints for the overall software organization. Let's start with the classic, maybe the most common one, client-server.
Client-server is one of the most widespread and fundamental architectural styles, forming the basis for much of the web and networked applications we use. Here you have distinct roles. Server blocks, or processes, or machines, are dedicated to offering specific services, like data storage, business logic execution, authentication. Client blocks interact directly with users, manage the user interface, and make requests to the servers to get those services.
So the client asks, the server provides.
Essentially, yes. Requests are typically made via network protocols using things like remote procedure calls, RPC, or more commonly now, web APIs like REST over HTTP. A key detail is that servers generally do not maintain intrinsic knowledge about their specific clients. The dependency flows predominantly from the client to the server. The server just responds to valid requests.
Then we have peer-to-peer, P2P, which sounds like a more decentralized version of client-server where everyone's kind of both a client and a server.
P2P is indeed a generalization of client-server. In this style, each participating block, or peer, can act simultaneously as both a client, requesting services from other peers, and a server, providing services to other peers. Think file-sharing systems or some blockchain networks.
More equal footing.
Right. Control flow between blocks is typically independent, except for specific synchronization needs when they interact. However, P2P systems are inherently more complex to design due to the possibilities of deadlocks in complex control flows and a much more dynamic, often unpredictable, network topology as peers join and leave. Dependency here can be bidirectional, which adds significantly to the complexity compared to client-server.
Another fundamental approach is layered architecture. This is organizing components hierarchically, like an onion or a cake, where each layer depends only on the one directly below it.
Correct. Components are arranged in distinct horizontal layers. The rule is typically that layer N can use services provided by layer N1, but cannot directly access layer N2 or below. And layer N1 should ideally not know about layer N above it.
What's the benefit of this strict layering?
This structure is highly effective for managing complexity and promoting separation of concerns. It allows layers to act as abstraction barriers. Upper layers don't need to know the details of lower layers. It also makes the system adaptable. You can potentially replace an entire layer, like the database access layer, with a different implementation, as long as it provides the same interface to the layer above. It's good for building systems that need to work across heterogeneous hardware and software platforms.
But there's a caution with layers, isn't there? You mentioned before too many layers can actually become a problem, adding overhead or making things rigid.
Yes, absolutely. You must be careful not to create excessive layers, sometimes called lasagna architecture. Each layer crossing can introduce a small amount of overhead, like extra method calls or data transformations. Too many layers can make the system slow, overly complex to navigate, and potentially difficult to change if a modification needs to cut across many layers. The success of the relatively simpler TCP/IP protocol suite compared to the more rigidly 7-layered OCISO model often illustrates this point. Sometimes pragmatism and fewer layers trump theoretical purity.
And a specific, very common application of that layered idea is the 3-layer architecture, or sometimes 3-tier if deployed on separate machines.
Right, this is a very common pattern, especially for business applications. It separates responsibilities into 3 distinct logical layers, which often map closely to our entity, boundary, control concepts. You have the interface layer, sometimes called presentation layer, responsible for user interaction containing boundary objects. Then the application logic layer, or business logic layer, containing control and entity objects, implementing business rules, processing, and validation. And finally, the storage layer, or data access layer, responsible for managing persistence, retrieval, and querying of objects, usually interacting with a database or file system. This clear separation helps maintain modularity and allows teams to specialize.
A truly classic pattern for interactive systems, especially GUI applications, is Model View Controller, or MVC. Everyone seems to know this one, or at least have heard of it, especially in web development frameworks.
Yes, MVC is incredibly widely recognized and influential, specifically designed for systems where the user needs to interact with data, potentially through multiple different presentations or views of that same data. It cleanly separates concerns into 3 distinct components.
Okay, what are they?
The model. This manages the application's data, state, and business logic. It's the core of the application, representing the underlying reality. It knows nothing about the UI.
The brain and the data.
Exactly. The view. This is responsible for presenting the data from the model to the user. It's what the user sees, the UI. There can be multiple views for the same model, e.g. a table view and a chart view of the same data. The view should ideally be fairly dumb, just displaying what it's told.
The face.
Right. And the controller. This acts as the intermediary between the model and the view. It handles user input from the view, interprets it, translates it into actions for the model, like updating data, and selects the appropriate view to display based on the outcome or changes in the model.
The traffic cop again, managing the flow.
Kinda, yeah. It manages the interaction flow.
And how do these components interact given that strong separation? If the model changes, how does the view know to update?
That's a key point. Changes in the model state typically propagate to the views via some kind of subscription and notification protocol, often using the observer pattern we discussed earlier. The views register interest in the model, and the model notifies them when something relevant changes, without the model needing direct knowledge of the specific views. This crucially decouples the model from the views, and also often decouples the controller from the view regarding data updates. The view and controller tend to change more often than the core model, so separating them makes the system much more adaptable.
And MVC has been adapted for the web too, right? How does that typically map since the view is often in a browser far away from the controller and model on a server?
Yes, it's been very effectively adapted. In a typical server-side web context, the view often resides in the browser, rendered as HTML, CSS, and maybe some JavaScript, displaying the user interface. The controllers typically reside on the server, processing incoming HTTP requests, interacting with the model, which might be application objects talking to a database, preparing the data, and then selecting and rendering the appropriate view template to send back to the browser.
Right.
More modern approaches like single-page applications, SPAs, using frameworks like React, Angular, or Vue represent as evolution. They shift much more of the application logic, including sophisticated view rendering and sometimes even controller-like logic, directly into the browser using JavaScript. This often involves fetching raw data from back-end APIs, which might still follow MVC or similar patterns internally, and handling the UI updates entirely client-side, reducing network latency and creating a more fluid user experience. But the core principles of separating data, presentation, and interaction logic remain influential.
Now, let's talk about how the scale and structure of backend services themselves have evolved, moving away from single large units towards smaller, more distributed ones, starting with the traditional monolithic services.
Right. The monolithic architecture is characterized by building an entire application as a single, large, unified process or service. While it might be modular internally, using classes, packages, etc., the entire application is deployed and runs as a single unit.
What are the downsides of that? It seems simpler initially.
It can be simpler to develop initially for small applications, but monoliths often impose significant limitations as they grow. Scaling usually requires replicating the entire monolith, even if only one small part of it is the bottleneck, which is inefficient. Delivery processes can become centralized and bureaucratic, making continuous integration and deployment CI/CD slower and more complex, as any small change requires rebuilding and redeploying the entire thing. And critically, a single bug or failure in one part can potentially bring down the entire application. Technology choices are also often locked in early.
Right, less flexible. And to address those limitations, we saw the rise of service-oriented architecture, SOA, a while back. How did that try to improve things?
SOA proposed a design based on breaking the monolith down into reusable, more loosely coupled components that offer remote services via standard interfaces and communication protocols, like SOP, WSDL, or sometimes REST. A service in SOA was envisioned as an independent unit of business functionality, potentially quite coarse-grained, designed to be reusable across different applications within an enterprise.
So breaking it down, but maybe into bigger chunks than microservices.
Often, yes. SOA emphasized establishing standard protocols for service publication, location discovery, and access, often leveraging middleware like an enterprise service bus, ESB, for integration, message routing, and transformation between services. SOA aimed for reusability and integration at a larger enterprise scale.
Which then evolved, or perhaps reacted against some complexities of SOA into the wildly popular microservices architecture.
This is everywhere now, isn't it? Everyone seems to be doing microservices or wanting to. Microservices are definitely a dominant trend, heavily influenced by web giants like Netflix and Amazon, and enabled by cloud technologies and practices like DevOps. They involve building applications as a suite of small, independently deployable services, each running in its own process and communicating typically over a network, often using lightweight mechanisms like REST APIs. Each microservice is organized around a specific business capability.
What are the big advantages driving this trend? Why are they so popular?
The advantages, when implemented well, can be significant. Granular scaling is a huge one. You only need to scale the specific services that are bottlenecks, not the whole application. Technology diversity. Different services can be written in different languages or use different databases, allowing teams to pick the best tool for their specific job. Team autonomy: small, focused teams can own and evolve their services independently, facilitating faster development cycles and continuous integration delivery, CI/CD. Resilience or partial failure tolerance: one service failing shouldn't necessarily crash the entire application. Other parts can continue functioning. And it allows for easier replacement or optimization of individual services without impacting others, as long as the API contract is maintained.
That sounds like a dream for development. But there are always caveats, right? It's not a silver bullet for every single problem, is it?
Definitely not. Adopting microservices introduces its own set of complexities. It's a distributed system, which is inherently harder to manage than a monolith. You need careful data management strategies to handle consistency across services, avoiding tight coupling through shared databases, and prioritizing communication via well-defined APIs. It's generally not recommended for systems with highly complex distributed transactions that require strong consistency across many services, or when network communication latency is a critical performance factor. The operational overhead of deploying, monitoring, and managing potentially hundreds of small services can also be substantial if you don't have mature automation and infrastructure, like container orchestration with Kubernetes. It requires significant organizational and technical maturity.
Good points. Other architectural styles often focus specifically on how parts communicate, like message-driven architectures.
Right. Message-oriented architecture is ideal for distributed applications that can benefit from asynchronous communication. Instead of direct calls, clients and servers communicate indirectly through an intermediary, usually a message broker or queue, like RabbitMQ, Kafka, or Azure Service Bus. Clients send messages to a queue, and servers consume messages from the queue at their own pace.
What does that buy?
This provides significant decoupling. Servers can be temporarily offline or busy. Messages will just wait in the queue. This promotes decoupling in both space. Clients don't need to know the specific server's address or even if it exists. And time. The client and server don't need to be online simultaneously. This greatly improves resilience and scalability for many workloads.
And a further enhancement or variation of that is publish-subscribe messaging. How's that different?
Publish-subscribe, or PubSub, enhances event handling and distribution on top of message-driven systems. Instead of sending a message to a specific queue for one consumer, systems publish events, messages, to a named topic or channel. Multiple interested subscribers can register to receive notifications of events published to that topic. The broker delivers a copy of the event to all current subscribers.
So one-to-many communication.
Exactly. This enables group communication, facilitates even looser coupling between producers and consumers of events, they only need to know the topic name, and allows for highly scalable and reactive systems where multiple components can react independently to the same event. Think stock price updates or social media notifications.
Finally, we have pipes and filters. This sounds like a factory assembly line for data processing, like you might see in Unix command lines.
It's precisely that model, a data processing flow. Each component, called a filter, reads a stream of input data from an input pipe, performs some transformation or processing on it, and writes its results to an output pipe. These pipes act as channels connecting the filters, defining the sequence of data flow. Each filter only needs to know the content and format of its immediate input and output data streams. It doesn't know about the filters upstream or downstream.
Where is this style used?
It's highly applicable in systems that involve transforming streams of data sequentially without much user intervention. Classic examples include chaining commands in operating systems, like catfile.txt, grep error, sort uniqueresults.txt. Data processing pipelines in ETL, extract, transform, load systems, or complex image or signal processing workflows. It promotes reusability and composability of filters.
And we should probably mention the opposite of all these well-designed architectures, the cautionary tale, the big ball of mud, the nightmare scenario for developers.
Yes, the big ball of mud is a well-known architectural anti-pattern. It represents a chaotic, seemingly unarchitected system that lacks clear structure, separation of concerns, high cohesion, or low coupling. It's typically a system that has grown organically over time, with code often slapped on top of existing code without careful design, becoming incredibly difficult, costly, and risky to maintain, understand, or evolve. All the architectural styles and principles we've discussed are specifically designed to prevent systems from degrading into such a messy and costly fate.
And why is understanding all these architectural choices, client-server, layers, MVC, microservices, etc., so crucial for our listener? What's the big picture takeaway here?
Because architectural choices fundamentally determine a system's key quality attributes. Its scalability, its resilience to failure, its ease of maintenance and evolution, the speed at which new features can be delivered, and even its cost over its lifetime. Appreciating these different styles helps you understand the strategic trade-offs made when designing the software systems you interact with every day. It helps you understand why some systems thrive under pressure while others crumble, or why some are easy to update while others seem stuck in the past. It's the difference between a building designed intelligently to withstand earthquakes and one that collapses at the first tremor.
So we've designed our systems, built our components, and structured them with elegant architectures and patterns. Now comes the critical, often undervalued, final stage, ensuring quality through software testing. Because what good is a beautiful design if it doesn't actually work reliably or meet the user's expectations?
Testing is indeed imperative, not optional. It's the intrinsic discipline within software engineering that aims to systematically evaluate and guarantee a system's quality and its conformance to specified requirements. To understand it properly, we first need to define some key terms that are often conflated in common language, but have precise meanings here.
Right, like the subtle but important difference between a defect, an error, and a failure. They sound similar, but are distinct stages in software problems.
Absolutely. A defect, often colloquially called a bug, is the underlying mechanical or algorithmic cause of a problem within the code itself, essentially. A mistake made by a human developer during design or coding.
The mistake itself.
Exactly. An error refers to an incorrect internal state of the system that results from executing code containing a defect. It's a state where execution could lead to a problem, a deviation from the correct internal state.
The system is wrong inside.
Right. And a failure is the observable manifestation of that error from the outside. Any deviation between the actual observed behavior of the software and the specified or expected behavior from the user's perspective or the requirements document, that's when the user actually sees something go wrong.
So a bug, defect, causes an error, or wrong state, which leads to a failure, wrong behavior. That clarifies it nicely. How do we manage these problems throughout the software development lifecycle? It's not just about testing, is it?
No, it's a multifaceted approach. Prevention is crucial, trying to avoid introducing defects in the first place. This is achieved through careful design practices, code reviews, inspections like walkthroughs or formal inspections, using complexity reduction techniques, employing static analysis tools, and having robust configuration management to avoid inconsistencies.
Stop the bugs before they happen.
Ideally, then, testing is the planned activity designed specifically to provoke failures by executing the system under controlled conditions with the intent of finding errors.
Actively trying to break it.
In a controlled way, yes. Debugging is the subsequent process of finding the root cause, the defect, of an observed failure or error, and removing it. Monitoring involves continuously collecting data on the software's state, performance, and error rates in production to detect problems proactively. And fault tolerance involves building mechanisms into the system, like exception handling, redundant components, or graceful degradation to minimize the impact of failures when they inevitably occur.
And there's that famous axiom or rule of thumb in software engineering. Finding defects early significantly reduces their negative impact and, crucially, their cost to fix. It's like finding a crack in the foundation of a house versus finding it after the roof is on and everything else is built. Much cheaper to fix early.
Precisely. The cost of fixing a bug discovered during requirements or design is orders of magnitude less than fixing the same bug found after deployment to customers. But we also need realism. As the famous computer scientist Edsger Dijkstra famously said, program testing can be used to show the presence of bugs, but never to show their absence.
That's a sobering thought. You can never prove it's bug-free.
Exactly. It's vital to recognize that complete, exhaustive testing of any non-trivial software module, testing every possible input combination and execution path, is mathematically impossible due to combinatorial explosion. Therefore, effective testing requires clear objectives, risk-based prioritization, and smart techniques and instruments to be effective and efficient in finding the most important problems with reasonable effort.
So how do you even design tests effectively? What goes into what you might call a test project or test plan?
A structured test project involves creating meticulous test cases. Each test case defines what specific functionality or requirement will be tested, when it will be tested in the lifecycle, and how it will be tested, including the specific steps to perform.
What else does a test case need?
It also specifies the necessary test artifacts. These include the prerequisite conditions, for example, system state, the specific input data to use, expected environmental conditions, and critically, the expected results or oracles, and often groups related test cases into scenarios representing realistic user interactions.
Oracles. That sounds mysterious, almost magical. What exactly is a test oracle, and why is it so essential for verification? You can't test without knowing the right answer.
Exactly. An oracle is essential for verifying test results. It's the mechanism, source of information, or principle used to determine the expected correct outcome of a test case, against which the actual observed outcome is compared. An oracle can be a human expert, a detailed specification document, a mathematical formula, another existing trusted system, or even a previous version of the software itself. Without an oracle, you run the test, get an output, but you have no way of knowing if that output is actually correct or not.
Makes sense. You need the answer. Key.
Right. And these test cases, especially the repeatable ones, can and often should be automated via test scripts or dedicated testing code. This automation is absolutely crucial for efficient retesting, regression testing, every time the code changes, especially in modern continuous integration and delivery CI/CD environments. Interestingly, as you alluded to, in agile models like extreme programming, XP, automated unit tests are strongly advocated to be written before the actual production code they verify.
That's a huge shift from traditional thinking. Writing the test before you even write the code it tests. Okay, let's talk about the different levels of scrutiny in testing, moving from the smallest pieces up to the whole system, starting at the bottom with unit tests.
Unit tests focus on the smallest independently testable units of code, typically individual classes, methods, or functions. They are primarily written and performed by the developers themselves as they write the code. The goal is to confirm that a specific code element was implemented correctly according to its specification and performs its intended functionality precisely, usually in isolation from other parts of the system, using mocks or stubs if necessary to isolate dependencies.
Okay, testing the tiny pieces work. Then once individual units seem okay, you need to see if they play well together when you connect them. That's integration tests, right?
Exactly. Integration tests focus on verifying the interactions and interfaces between groups of components or modules as they are combined. Developers also typically perform these tests to verify if the interfaces between components match up and if their collective architectural behavior functions as specified when they collaborate.
How do you test components together if some parts they depend on aren't ready yet?
That's where test aids like drivers and stubs become invaluable. A driver is a dummy piece of code that simulates a higher-level component, calling the component under test. A stub is a dummy piece of code that simulates a lower-level component that the component under test depends on, often just returning canned responses. These allow you to test integration points before the entire system is complete.
And there are different strategies for how you integrate and test, right? Like Big Bang versus more iterative methods.
Yes. Vertical integration approaches deal with the order. Big Bang integration tries to put everything together at once near the end and test it all. All this is generally high risk because finding the source of failures is very difficult. More structured approaches include bottom-up, testing lower-level utility modules first, then integrating upwards. Top-down, testing higher-level control modules first, using stubs for lower levels, then integrating downwards. And the sandwich method, which combines both.
And horizontally.
Horizontally, the modern prevailing approach is continuous integration, CI. Here, components are integrated frequently, often multiple times a day, as developers commit code changes. Automated build and integration tests run immediately. This enables much faster feedback, catches integration issues very early when they are easier to fix, and is a cornerstone of modern CI/CD pipelines aiming for frequent, smaller releases.
After individual units and their integration seems solid, we move up to testing the entire product as one entity, system tests.
Right. System tests take the complete integrated software or system as their object of test. They are often performed by dedicated testers, but sometimes developers too. The primary goal is to determine if the complete system satisfies all its specified requirements, both functional, what it does, and non-functional, how well it does it, as documented in the requirements specification or user stories. This is testing against the overall contract.
And there are different types of system tests, aren't there? Beyond just checking if the features work as described, like validating performance, security, usability, etc.
Exactly. We broadly categorize system tests. Functional tests, often conducted using black box techniques where you don't look at the internal code, validate the functional requirements. Does the system perform the functions described in the requirements or user manual correctly? Test cases are derived directly from those specifications.
Checking the what?
Yes. Non-functional tests, on the other hand, are crucial for validating the system's quality attributes or non-functional requirements, the how well. These include many subtypes. Performance tests, reinvalidable, stress tests, pushing system limits to find breaking points. Volume tests, checking behavior with large quantities of data. Time tests, measuring response times and throughput under expected load. Also, security tests, actively trying to penetrate the system, find vulnerabilities. Usability tests, checking ease of use with real users. Compatibility or configuration tests, ensuring it works across different browsers, OSs, hardware setups. Reliability tests, checking stability over time. Availability tests, measuring uptime. And recovery tests, how well the system responds to failures, errors, or data loss, and how quickly it can recover. Each of these uncovers different but equally critical classes of potential problems.
Finally, at the very end of the process, we have acceptance tests. These sound like the ultimate gatekeepers, where the clients and users themselves give the final thumbs up or thumbs down on the product.
That's essentially their role. Acceptance tests focus on the final product being delivered. They are primarily performed by the clients, customers, or end users, often in their own environment. The goal is to demonstrate that the system meets their specific business requirements and user needs, and is truly ready for operational use and deployment. It's about user confidence and sign-off.
Are there different kinds of acceptance tests?
Yes. Common subtypes include alpha tests, where the client uses the software early on, but typically in the developer's controlled environment, allowing developers to observe and fix issues quickly. And beta tests, which are conducted later in the client's own environment, usually without direct developer presence, aiming for realistic execution with real users and real data before the final release to the wider market. Feedback from beta testing is invaluable.
So beyond these major levels, unit integration, system acceptance, what are some other key concepts and techniques in the world of testing that every well-informed person should probably know about?
Well, we've already reiterated the critical importance of automated tests for efficient regression testing, especially in agile environments, and their crucial role in driving design when using approaches like TDD, where tests are written before the code.
Right.
We also often differentiate between static tests and dynamic tests.
Static tests are cool because you don't even need to run the code to find potential issues, right? Like spell checking for code.
Kind of, yeah. Static tests involve verification without actually executing the program code. This includes using static analysis tools that automatically scan source code for common programming errors, potential bugs, security vulnerabilities, or violations of coding standards. It also includes human review processes like peer reviews, for example, pair programming, code walkthroughs, formal inspections, where developers examine each other's code or designs.
Finds problems just by looking.
Exactly. Dynamic tests, conversely, absolutely depend on program execution. You run the code with specific inputs and check the outputs or behavior. Dynamic tests can be further categorized based on knowledge of the internals.
Like white box versus black box.
Precisely. Structural testing, often called white box testing, evaluates internal aspects of the code, like ensuring specific conditions, logical paths, loops, or statements are executed. This requires knowledge of the code's internal structure. Functional testing, often called black box testing, evaluates the software's functionality based solely on its specified behavior-checking outputs for given inputs, without needing knowledge of the internal code implementation. Test cases are derived from requirements or specifications. There's also gray box testing, which combines elements of both.
And there's a whole array of specific testing techniques too, right? For designing those test cases smartly, since you can't test everything.
Yes, absolutely. Since exhaustive testing is impossible, testers use various techniques to select a representative and effective set of test cases. Common examples include exploratory testing, simultaneous learning, test design, and execution, relying heavily on the tester's experience and intuition. Equivalence class partitioning, dividing the input domain into classes where inputs are expected to behave similarly, then testing one value from each class. Boundary value analysis, focusing tests on the edges or boundaries of those equivalence classes, as errors often occur at boundaries. Decision table testing, for complex business rules with multiple conditions. State transition testing, testing how the system moves between different states based on events. And path testing, attempting to design tests that execute specific paths or all paths through the code's logic, often guided by white box analysis.
Bringing it all together now, testing isn't just an isolated phase tacked on at the end anymore, is it? There are entire development approaches that integrate testing right into the core of how software is designed and built, making it a fundamental driver of quality and design from the very beginning.
Precisely. The thinking has evolved significantly. For instance, domain-driven design, DDD, while primarily a design approach, strongly emphasizes building a deep understanding of the business domain through collaboration and modeling. This deep understanding directly informs and guides all design and testing activities, ensuring the software truly reflects and correctly automates real-world business processes and rules. Tests in DDD often focus on validating the core domain logic.
Then there's the famous test-driven development, TDD, which we mentioned earlier, which is all about writing tests before the production code. That sounds radical, but seems very effective.
TDD completely inverts the traditional order and has a profound impact on design. The development cycle is famously known as red-green refactor. First, you write a small, automated test for a tiny piece of functionality you haven't implemented yet. Naturally, this test fails. That's the red light. Second, you write just enough minimal production code to make that specific test pass. Now you get a green light. Third, you look at the code you just wrote and refactor it to improve its design, clarity, or efficiency while ensuring all tests remain green. Then you repeat the cycle for the next small piece of functionality.
So the tests drive the design.
Exactly. TDD forces you to think about requirements and interfaces before implementation, leads to highly testable code by design, provides a safety net for refactoring, and results in a comprehensive suite of unit tests. It's a core practice of extreme programming, XP, and significantly improves code quality and developer confidence.
And then building on TDD, we have things like behavior-driven development, BDD, and acceptance test-driven development, ATDD. These seem to focus even more on collaboration and clear communication about requirements using tests.
Exactly. BDD emerged from TDD, aiming to improve communication between developers, QA, and non-technical stakeholders, like business analysts or product owners. It describes expected system behavior using a structured, natural language format, like Gherkin's given when-then syntax, that everyone can understand. These behavioral specifications often double as automated tests, bridging the gap between business understanding and technical implementation.
So the requirements are the tests, almost.
In a way, yes.
Yeah.
And ATDD is very similar in spirit. It's a collaborative practice where the team, developers, testers, business folks, defines acceptance criteria for user stories using concrete examples. And these examples are then turned into automated acceptance tests before the feature is implemented. The goal is to create clear, unambiguous, executable specifications of the software, ensuring everyone agrees on what done means.
So the ultimate why behind all this rigorous testing, especially these integrated approaches, isn't just about squashing bugs after the fact, is it? It's about so much more than just finding errors.
No, it's far more profound than just bug hunting. Testing, especially when integrated deeply into the development process through approaches like TDD, BDD, and ATDD, is fundamentally about building the right product and building the product right. It's about ensuring the software built truly aligns with business needs and user expectations from the start. It actively drives better design decisions by forcing consideration of testability and requirements up front. It acts as a continuous feedback loop for developers, provides living documentation of system behavior, and ultimately builds unwavering confidence in every single release. It's the ultimate guarantor of software quality, fitness for purpose, and maintainability.
Wow, what a journey. We've just taken a really deep dive into the foundational thinking that shapes every piece of software you interact with. We started with the blueprint of code, understanding how models like data flow diagrams and UML help us visualize and specify complex systems before we even write them. It's like having X-ray vision for software architecture.
Yeah, getting that initial structure right is so key. Then we truly dissected the very building blocks of software, exploring how classes are identified from requirements, how they can be categorized using stereotypes like entities, boundaries, controls for better organization, and how they relate through fundamental connections like associations, aggregations, compositions, and the often tricky inheritance. We saw how crucial defining these relationships clearly is for structural integrity and long-term maintainability.
And we didn't stop there. We delved into the guiding principles and proven design patterns that elevate software from merely functional to truly robust, flexible, and adaptable. Principles like keeping things cohesive, minimizing coupling, and the formidable solid principles SRP, OCP, LSP, ISP, DIP, along with practical patterns like strategy, observer, and singleton, show how experienced engineers solve recurring problems elegantly and efficiently, avoiding common pitfalls.
Right, these aren't just academic theories. They are practical tools learned from decades of building software. Finally, we explored the indispensable world of software testing, moving through the different levels from focused unit tests, verifying small code pieces, to integration tests, checking collaborations, system tests, validating overall requirements, and finally, acceptance tests, ensuring user satisfaction. We saw how quality is systematically built in and verified.
And we saw how modern approaches like TDD and BDD weave testing directly into the development fabric. Not just for finding bugs after they're made, but for actively driving better design and fostering confidence in what's being built from the very beginning.
Exactly. Testing becomes part of the design process itself.
So for you, our listener, you now have a comprehensive framework for understanding why some systems are resilient, adaptable, and maybe even a joy to maintain, while others seem brittle, resist change, and falter under pressure. It's truly fascinating when you start to see these concepts: good modeling, clear relationships, solid principles, thorough testing in action, consciously or unconsciously in the software all around you.
So here's maybe a provocative thought for you to chew on as we wrap up. Consider a piece of software you use daily, perhaps your favorite streaming app, a productivity tool you rely on, or even your online banking portal. How might the concepts we've discussed today, like low coupling versus high coupling, the separation of concerns, maybe using MVC or entity boundary control, a specific architectural style like microservices versus a monolith, or even a particular design pattern like the observer pattern handling updates explain its strengths, its weaknesses, or even some of its annoying quirks?
Could understanding these principles help you better articulate improvements for such software, or perhaps even contribute more effectively to its design or troubleshooting if you ever had the chance? Start observing the software around you through this new lens of engineering principles. It'll definitely spark even deeper curiosity and, I think, a whole new appreciation for the intricate, intelligent world of software engineering that happens behind the screen.